can't do 30 more push-ups. All right, Nandini, over to you.
Yeah, thank you. Hello, everyone. How are you doing? So I'm going to be talking about Ruby meet the Metaverse. So what does it mean, like Metaverse, and like how many of you, I want to know, have built any multiplayer games? Not in Ruby, just any language. Show of hands. Okay, only one. Okay, so maybe this talk will be more enlightening for you if you have not built any multiplayer games. And I'm assuming you've not built it in Ruby, the person who raised it. Okay. So I think this talk will be exciting then because you will learn something new from this talk. So hi everyone, my name is Nandini and I'm a principal engineer at Oracle. My background is Java and I'm a Java developer, but I've been tinkering around in Ruby for quite some time now and I wanted to explore. So my background is distributed systems and concurrency. So I wanted to understand how exactly do you solve those problems of concurrency and race conditions in Ruby. And that's where I'm going to show you exactly what you can achieve with Ruby's concurrency models. So the talk is going to be a mix of technical and fun. So just be on the lookout for a demo that's going to come. Hopefully you won't feel it's boring. Okay, so what does building a real-time multiplayer game mean to you, right? So let's look at some existing games that we have. One such game is like a shooting game, right? In which there are different players and they are targeting some world objects. World object could be like a building or you have some person that you're trying to shoot. So there are players who are connected to the arena and then you are having some movement from the players. So, player 1 could be taking a step forward. Player 2 could be, shooting the person or shooting the building. So the building here is like a world object and that world object should be reflected to everybody. Because if other person is also looking at the building and if person A has shot down the building should get destroyed, right? I mean, the building should not be okay. Only person 2 is seeing the building is destroyed and the person 1 is seeing the building is intact, right? So the state needs to be consistent here. Let's look at another game. This is a Minecraft game where, different avatars are trying to, let's say, build or mine something, So in this also, if you see the commonality between these two games, there are different avatars and they are doing some action and there are some world objects. In this game, the world object is a farm where they're doing the farming. And once the farm has been built, the farm needs to be built for all the players, right? So there are some common features, if you notice, between all these multiplayer games from a developer perspective. What you see is just the UI, but the actual backend logic is pretty similar. Now let's look at what is similar exactly. So if you have a real-time multiplayer game, you will obviously need multiple players who will be connecting to that game, right? And there will be a need to have real-time synchronization between these players. So these multiple players will be connecting simultaneously to the game, and we need to synchronize their actions in real time, meaning that each action that any player takes effect instantaneously. And everybody should see that action happening at the same time. This is called a strong consistency. And we should also maintain the, So we are basically processing multiple inputs. There should be no corruption of data that, okay, the backend crashed because, two people tried to destroy the same building at the same time. Or one person shot the other person, but the other person did not die. And he resurrected automatically. This is called data corruption. Another thing would be that the game world state, which we already talked about. And the last thing is performance. Because, as many people join the game, you don't want your game to slow down or crash just because so many people are joining. So these are some important characteristics of a multiplayer game. And if you look at any game, it has all these characteristics. So don't focus on the UI because the UI could be anything. It could be different avatars, it could be a cookbook, it could be a shooting arena, it could be a Minecraft, but the backend has these features and characteristics. So when you're building this kind of a game, what, what are the challenges in that game? So I think we talked about some of them, that there should be a lot of players connecting to the game, first of all, and everybody should see slow latency. So if I connect to the game and I'm just waiting that, oh, when will my turn come, then I won't enjoy the experience, right? So I need to see real-time effect when playing that game. The second thing is that there should be no race conditions. Like I already said that if I go and destroy a building and somebody else comes and also destroys the building and there is some race condition and the building itself, like let's say, vanishes or the explosion doesn't show up, then it's not going to be a consistent state. So yeah, these are the different problems. Now let's look at how do you solve these problems in Ruby. So if you were to build this game in Ruby, would you be able to do it? And if yes, how? So I think that's what we are going to see today and see how we are going to achieve that. So traditionally, Ruby has been criticized for concurrency limitations because of the GIL, which is the Global Interpreter Lock. So what does that mean? It means that if you have multiple threads, and if you create threads, actually at the CPU level, only one thread gets executed. So you're not really achieving CPU parallelism. So we have in Ruby, there are a few different models for managing concurrency. Each one has trade-offs in terms of scheduling, isolation, performance, and complexity. We have threads, we have fibers, we have processes, and we have reactors, right? So everybody knows process and threads, I believe. Show of hands for who knows processes and threads. Okay, I see that's a pretty good number. So at the highest level, everybody knows process is like a heavy weight. It's fully isolated, completely independent. Threads are lighter, but they share the memory, which can cause race conditions, so you have to be very careful when designing your code. Fibers are even lighter, and they give cooperative multitasking within a thread. Reactors bring true parallelism with safe isolation through message passing. Let's start with fibers. So what is fibers? Let's take an example here. Fibers are lightweight units of concurrency. They run in a single thread. So if you look at time, the actual thread that gets executed is only one. But execution switches only when you explicitly yield. So in your code, you would write fiber yield. And at that time, the execution will switch from one fiber to the other. But on the CPU level, only one fiber gets executed. So what scenario is this fit for? They're good if you want fine control, like lightweight task, state machine, and you don't need full parallelism. So if you're making an API call, you just make the API call and then do a fiber yield, and then you go to another fiber, and then when you come back, your IO task is done. So you utilize your parallelism. On the other hand, you have reactors, which are completely different. Reactors implement the actor model, and they have isolated memory spaces. They can only communicate through message passing. So this is a different form of threads, but these have message passing. So they don't have any sort of shared state. But fibers are not executable in parallel. Reactors execute in parallel. So if you can see here, reactor A, B, C, they can all execute simultaneously on different CPU cores. The isolation is by design, and it eliminates race conditions, because reactors can't share mutable state. They can't corrupt each other's data. This makes reactors perfect for managing our game state, because the game state is something that everybody will be seeing, and it cannot be inconsistent for different people, right? So consistency is very important for the game state. Now let's see how we combine these concepts and build our game architecture. So at the top, we have our browser clients, which are connecting via web sockets. And the web sockets layer is handled by our connection manager, where each player connection runs in its own fiber. So we will create a fiber connection for each player, And we'll also have a cleanup fiber, which is like when you have a player which disconnects. So if I'm a player, I join the game, I drop out. So when I drop out, my connection data needs to be cleaned up. So that cleanup will be done by a cleanup fiber. And then we would have the message passing layer. All the game messages, Ractor messages are going to be passed by this. And then we have our world state Ractor, which maintains the actual world state of the game, like the player positions, to detect collision, and any chat messages if people are chatting with each other during the game. So notice that we're using each concurrency primitive for what it's best. Like we're using fibers for IO-based concurrency, and then Ractors for CPU-bound state management. Each layer is handling different aspects. So yeah, we talked about this, which is like fibers is for IO-heavy cooperative scheduling, and Ractors allows us to maintain a single source of truth for the game state. Let's look at our data model. This is beautifully simple. So we have players with their positions. If you see, the ID is the ID of the player. The XY indicates the coordinates of the player. And then the last scene time, you can have other attributes like the avatar. And then you can have the world state, which has a list of all the players, the chat messages, the world boundary, where players cannot go out of that boundary of the game. And each player is connected via a connection which has a fiber WebSocket. So this is like our data model, and let's now get into the actual bit where I think everybody is looking forward to, the code. So this is our connection manager. Notice how clean this is. We initialize with a reference to our world Ractor, and we maintain connections and metadata. So the magic happens in handle connection. Each WebSocket connection gets a new player ID, and then we use WebSocket.each message to basically manage a fiber-based async WebSocket gem. We don't need to create fibers manually, but the gem handles that for us. The key point is the error handling. Notice that in the error handling, if a player disconnects, you need to do the cleanup of that player and remove the connection from our connection metadata. Then let's look at the world state Ractor. The world state Ractor is where we maintain all the game state. So notice the game state is a list of all the players, the world objects, the chat messages, the world boundary, and the game stats, like how many players have joined, what messages have been sent, and so on and so forth. You can enhance this to any sort of advanced game that you're playing. And the core loop is very simple. Receive a message, pattern match on the type, and then handle that. Notice that the handle player, like when a player joins or player leaves, we just update our state. So the state needs to be updated that, okay, this player has joined, and what is the message being sent, and this is the implementation of the handle player join. So what happens is this Ractor.yield method that's called, where we broadcast the change to all the connected players. This is a push model in action. The moment a player joins, all other players are notified. So in the game, you will see that when new people join, like everybody will be notified in their world Ractor state that the player state has changed. So this is how we have basically pieced independent components together. Of course, this is not the entire code. The entire code is on GitHub for anybody who's interested. So this is the process world state, and excuse me. So the end-to-end data flow is basically what happens is the browser first sends a WebSocket message. The connection manager receives it in a fiber, validates it, and then sends a message to the world state Ractor. And then notice that the Ractor processes the move and then updates the player position and yields the update. Our update processing fiber catches this immediately and broadcasts the new position to all the clients. So The result is that we have a strong, consistent model. So this is not a eventually consistent model where, at the end, everybody will see the same state. We are immediately making sure that as soon as a state change happened, everybody is notified. There's no race condition because everything goes through the single reactor, the world state reactor. No complex locking mechanism is needed, and it's super fast because everything is sequential within the reactor but parallel across the system. Basically, we have decoupled the players from the world state. So, yeah, this is the overall thing. I think this is what everybody is kind of looking forward to, the demo. So let's go ahead. So notice that there are a lot of people who are connected here. These are the active players. So there's Nandini, Raj, Kiran, Akanksha. And then there are world objects which are getting generated. So there are treasures, there are portals. And as soon as a user or a player goes on that and obtains that world object, that is notified that, hey, you collected a portal, Priya collected a power-up. So this is a very simplistic game that we've built using Ruby, but you can basically improve the UI and achieve like more cool results. This is an in-memory implementation, so there is no database. So what I've done is basically, I just hosted the game on my local host and opened like 10 windows. So there are 10 different players who are connected to this game and playing this. But I'm not hosted it on a web hosting portal or anything. The code is available on GitHub for you to go around. I basically am moving my cursor in real time, and this is all a single Ruby process. And the game is like strongly consistent. I already told you there's no race conditions which are possible. Sorry. So why does this matter? Like, why do I care about this game? Like, you people might ask. I'm not seeing why this is important. So this is not just relevant for games. This is also applicable to real-world business applications, because think about collaborative platforms. Let's say Google Docs. Let's say talk about Figma, right? They all need the same real-time synchronization we just built. Because when multiple people edit a document simultaneously, you need the exact same consistency guarantees we implemented for this game. Financial systems are another area where this would matter. Live commerce, IoT, monitoring systems, everybody is basically needing this kind of synchronization. And synchronization, I believe, is the most fundamental problem in like computer science that needs to be solved. And understanding how different languages solve it is something that I always look forward to learning. So how to make this code prod ready? Like, is this code that you developed prod ready? No, of course not. Connection drops are inevitable. Like, users can just close their browsers. Networks can fail. And then device can just sleep when your game is on, right? So we have a disconnect player method which cleanly removes the player from all the data structures in memory and notifies the other person that, hey, Alex left the game. Invalid messages can also happen, so you have to make sure that you're handling malformed JSON or doing exception handling. What if our world state reactor crashes? In production, you need monitoring of the fibers that watch for the reactor failures. If the main reactor dies, then what happens? Then we spawn a backup and we recover the state from the last good snapshot. So you would need to store the state in the database at that point. So this is what you would need to make the code like prod ready. So of course, it's not like prod ready at the moment. Now the question comes, how to scale this code? So the number of messages that are flowing through are enormous, right? Because every single step when the player takes a movement of the position, it's a message. It's a JSON message that's flowing through and getting updated in the world state reactor. So it's obviously not efficient. So we can obviously batch process those messages, because if they're happening at a nanosecond granularity, then we can do some batch processing to improve the speed. We can also separate the read-write reactors. Right now, the world state reactor is a single reactor. We can have two different states, one just for reads and then one for the write, and the write will at some periodic frequency update and then propagate that to the read reactor. And then you can also have different reactors for different game arenas. For example, if there is a game which is so huge that there are like multiple buildings and there are multiple like cities in the game, then different arenas of the game can be managed by different reactors to not have bottlenecks in the code. And then, of course, you should horizontally scale your Ruby process. With multiple Ruby processes, you should host it on some machine, and you can have a load balancer and then route the request so that the number of connections connecting to one single Ruby process is not more than the allocated supported number for that particular hardware. Yeah, so I think this was the conclusion, and I was trying to understand like how this differs from Java. And I mean, this is my take on how Java is as compared to Ruby with respect to concurrency and parallelism. So what I've understood is that for Java, you have a shared memory system where you can manage the state in a shared memory, and you can have synchronization. It could be blocking or non-blocking. But there are race conditions possible because your code needs to be like correct. You need to make sure that there's no deadlock, and this could be hard. Like the debugging in Java is going to be hard if you have a complex code. But reactors inherently do not have any races because there's only message passing. There is no shared state. So yeah, this is like a summary of what my understanding is Java versus Ruby. So yeah, that's it. Thank you. This is the link of the GitHub repo, and then you can connect with me on LinkedIn. Thank you.